This is a video response to Khan Academy's video on microstates and macrostates. And I'm making it because I liked the Khan Academy video, but there were a couple things that I'm unsure about. So, in that video, Salman said, suppose we have a piston, like the one I have here, and I've made it so I can drag it up and drag it down. And it says we've got it sitting here in equilibrium, and we have maybe some gas on the inside of this guy, and we have on top a heavy rock that's holding it down. And suddenly we make half of the rock disappear. So I will try to do that. Okay, half of the rock disappears, and now what happens is this piston starts shooting up and goes back down and oscillates. So that's an excellent description of what happens. And it comes to some new equilibrium up here. Now the point of Khan Academy's video was that while the piston is going up and down, the piston is not in thermodynamic equilibrium, and therefore the macrostate is not well defined. Now first, I want to make sure that the language I'm using is that a macrostate is not the pressure or the volume or the temperature. The macrostate is all of those thermodynamic variables considered jointly. So pressure and volume and temperature and any other important quantities such as the chemical composition or the mass of the system, all of those things combined are one macrostate. Now the claim was that if those things are changing, they're not well defined. That's not at all obvious to me, because there are plenty of things that we can look at in the universe that are changing and are well defined. For example, the position of an object. Well, the position of an object changes, that's its velocity, but it's certainly well defined. So in this case, if we look at, say, the volume of this piston, even if the thing is moving up and down, I would disagree with the statement that the volume is not well defined. The volume is actually very easy to define. We simply trace around the outside edge of this guy and see how much space is in there, and that's the volume, whether it's moving or not. But temperature and pressure, yes, that may be not well defined. So what does pressure mean? So here's what I think pressure means. What I'm going to do is I'm going to grab this other small piston and bring it in here. So now if I take a very small piston and put it inside my big piston, and everything's in an equilibrium state, then what's going to happen is when I move the small piston in here, it'll adjust itself until the pressure inside the piston is the same as the pressure inside the small piston is the same as the pressure inside the big piston. And that way, by seeing where the level is on this small piston, measure the pressure inside the big piston. Okay, so if I move the big piston up some, then the pressure will drop inside here, and the pressure on the small piston will go up. Now, I think what we're saying when we're saying pressure is not well defined is not the fact, merely the fact, that pressure is different at different parts in the cylinder. For example, if this is in a gravitational field, which it evidently is because I have this block up here and the block is pulling down on the piston, so there must be some gravity. If it's in a gravitational field, then any object inside the piston, experiences buoyancy. It does that because there's a pressure gradient inside there. In equilibrium, the pressure is different at different parts inside the piston. So the mere fact that the pressure is different at different points does not make the pressure ill-defined. What I think is happening with the pressure being ill-defined is that if I take this little piston, and even if I damp it critically, so that when the pressure changes outside, the pressure in the little piston adjusts as quickly as it can, as I'm taking this guy and swinging him up and down, if I looked at this little piston, it would be shaking, and I would have a hard time determining what the pressure is inside this little piston. Furthermore, if I moved it to a spot that was nearby, even though that spot is nearby, it may read a different pressure in a spot that's a little bit to the right. And furthermore, if I take this guy and rotate it, let me see if I can rotate it. Oh boy. Well, okay. I'm failing with technology at the moment. But if I take this guy and rotate it, I may find that even if I leave it in the same spot but rotate it, the pressure is changing as I do that. And in those cases, I think you might say, well, the pressure is ill-defined. As for the temperature, if we look at the temperature, well, the temperature is the average kinetic energy of the molecules that are in there. So let's say this piston is on its way down at the moment. And so what I'm going to do, I'll draw in a little vector here, and it shows the piston is coming down. Okay, so then what are the air molecules doing while the piston's coming down? Well, there were some air molecules up here where the piston just came through, but those have all been hit by the piston, and so they're being pushed down. And so I have a high density of air molecules up here underneath the piston, and a low density of air molecules everywhere else. So for one thing, the pressure is going to be higher up here. But for another thing, these molecules have just been impacted by the piston, and so they're going to have higher velocity on average, and they're going to have higher temperature on average. Furthermore, we expect when something is at an equilibrium that the atoms inside there, their velocities will be, or their energies, will be distributed according to some standard statistical distribution. So, for example, their energies might follow a Boltzmann distribution. But if you just smacked all these molecules up here with a bar, they're probably not going to have that statistical distribution anymore if you do it quickly. They won't have time to interact with each other a lot and partition their energies the way they would like to be at equilibrium. So now certainly it's not true that the thing has to be perfectly at equilibrium in order for the macrostate to be well defined. If that were true, then nothing would ever change. We can never measure macrostates while the thing is changing, because it won't change if it's in equilibrium, and so we could never have an expansion or a contraction or a change in temperature. What needs to happen is that the expansion or contraction or change in temperature needs to be slow. Slow compared to what? Well, in this case, I think it might be that the time that it takes the piston to move, say, one mean free path of a particle, if that's a short time compared to, say, the period of the fundamental mode of a standing sound wave in the piston, well, then certainly that's going to be slow enough for us to be able to define the macrostate. But I just wanted to say that I think the picture is slightly more complicated than simply stating, well, whenever something is out of equilibrium, the macrostate is not well defined because it might be different in different parts. I think there's a little more to it than that. I'm not sure that I totally understand what does and doesn't make a macrostate, but I just wanted to throw that out there as food for thought.